Hello guys, welcome to Rental Solutions and welcome to your Grade 12 Physical Sciences, your lesson on momentum and impulse. Today specifically, we are looking at impulse. Okay, we've been saying momentum and impulse forever. Now we are looking at impulse. Okay, today we are looking at impulse. All right, so as is usual, we have to introduce the concept, tell you what it's about if possible, and the relevant formulae or background that we have done in our introduction and revision. And then we will proceed to get to impulse momentum theorem. And then we will show you the use of impulse in safety designs. Lastly, we complete the video with wet examples. I'm hoping to make it less than 45 minutes. I'm hoping, but I will see. However, I don't want to rush through items. We are going to take them slowly. All right, without any waste of time, let's get into it. So, in our introduction, let's begin. So, by now, you know what is momentum, right? We said momentum is, momentum of an object is the product of the mass and the velocity of that object, all right? And then we spoke of change in momentum, and obviously, change of momentum or change in momentum. When we talk of change in momentum, obviously we say final momentum minus initial momentum. That will be your change in momentum, all right? Which is delta P. Delta P is change in momentum. Of course, we have summarized this to say it is product of the mass and the difference in the velocity of the final and initial velocity, right? And then we also have Newton's second law of motion, right? We also have Newton's second law of motion in terms of momentum, right? Of motion, not of momentum. Newton's second law of motion and momentum, right? It gave us the formula F net equals delta P over delta T, right? In this section, we are not going to deal with, what is this? Conservation of linear momentum. But as a reminder, let me note it down. And of course, in this chapter, we have dealt with conservation of linear momentum. All right, we have dealt with conservation of linear momentum. All right, which says mass of A, V, AI, plus a mass of B, initial velocity of B is equal to mass of B multiplied by its initial velocity. And let me start with A, mass of A multiplied by the final velocity of object A, plus mass of B multiplied by the final velocity of object B. This was your law of conservation of linear momentum. Right? Perfect. Again, we also spoke of elastic collisions. We said if collisions are elastic, both the total momentum and total kinetic energy will be conserved. So basically, the most important, because we assume in this section that momentum is conserved, will be total kinetic before collision. So let me call it I is equal to total kinetic after collision. Let me call it F. And then if it's inelastic, only the only thing, linear momentum will be conserved, but the kinetic energy will not be conserved. So for inelastic collisions, we said total kinetic energy before collision will not be equal to total kinetic energy after collision, right? So these are the things that we said. Okay, these are the things that we said, and we are going to now proceed. Now, for the section that we are dealing with, I want you to imagine this. I want you to imagine this. Imagine if we did not have, I'm going to write them. Imagine if we did not have airbags in our cars. Let me add seat belts. I'm going to also add crumple zones. Okay, I'm going to add crumple zones. I'm going to add arrestor beds. I'm going to add arrestor beds. I'm going to add air mattresses. This one I must say I have to add, for example, Olympics and Stancemen. Okay, Olympics, Houston Olympics and Stancemen in your action, no visa. Alright? So Stancemen. Okay, and what else? I'm gonna say padded goalkeeper gloves. Padded goalkeeper. Oh yeah. Padded keeper gloves, because you don't have goalkeeper in cricket. Padded goalkeeper gloves. Shin guards. Shin and leg guards. Let me say that. Shin and leg guards. We also talk helmets. Alright, we also talk helmets. And then padded bat or racket handles. Alright? Padded bats or racket handles, and so on. Right? So, I want you to consider these items that I just wrote here. That, remember, I'm asking you, what would happen basically if these equipment or items were not like I'm mentioning them? For example, let's talk now if we did not have airbags, seatbelts, crumple zones on our cars, if we did not have arrestor beds, if we did not have all these air mattresses. I think this should be, I don't know, I saw in one picture it said it's arrestor as in like T-E-R, and I'm like, why T-E-R? Is it better if we say T-O-R? So I'm going to go with T-O-R if it's bad spelling the time. So we have to ask ourselves why in Olympics, I think it's high jump, why they fall onto mattresses, and even whatever jumps and whatever, I don't know what they called, why are they falling onto mattresses and not onto the ground, right? And Stancemen, why are they falling on the ground, on what is this, air mattresses and nets, and not on the ground? He will answer those questions later. Okay, so all these are safety design features, or all these are, what are they? They are safety design considerations. They are safety design considerations. All these are safety design considerations. Alright? For safety, to prevent injury, all these things are the way they are. Alright? We'll explain them later. Right. Perfect. Moving on. Let's get to the second part of our video. In our second part of the video, we will talk impulse momentum theorem. Momentum theorem. So we're talking impulse momentum theorem. From Newton's second law, right? From Newton's second law of motion, from Newton's second law of motion and momentum, right? And momentum, we had this formula. F net equals delta P over delta T. So when you cross multiply by delta T throughout, you will be getting F net delta P equals, F net delta T, pardon. F net delta T equals delta P. This part here, we term it impulse. Okay? We call it impulse. Okay? Remember, I'm saying F net delta T is impulse. Remember, guys, you somehow have known this formula, or you know this formula by now before getting into this video. You have come across this formula. And now, we're calling the product F net delta T impulse. Right? We're calling it impulse. Okay? We're calling it impulse. Now, let's define this impulse. So, impulse is basically the product of the net force, acting on the object. Acting on the object. Let's go back to the previous page. Product of the net force and the time interval. If you guys recall, that was delta T. Oh boy, come on, buddy, please don't do this. Product of the net force. Okay, let's wait for it. So it is product of the net force acting on the object and the time interval during which the net force is acting on the object. So it was F net times delta T. He's back. So let's continue. Impulse is the product of the net force acting on the object and the time interval, and the time interval during which the net force is acting. During which the net force is acting. Okay, so that is impulse. Okay, guys, that is impulse. So we're saying impulse in the product of the net force acting on the object and the time interval during which the net force is acting. So, anyways, impulse in width is F net delta T. Okay. It is also a vector quantity. It's a vector quantity. Okay. Meaning it has magnitude and direction. Right? And obviously, impulse has the direction, is in the same direction as your net force. Okay? It is a vector quantity. It has SI units. It has unit. What is the unit? Newton times second. Okay? Newton second. There is the unit of impulse. SI unit of impulse is Newton second. Okay, so now we're saying 1 Newton per second. Let's see, what is Newton? If I were to dissolve Newton, it is kilogram. It is kilogram meter per second squared times this guy. What is this? This will become 1 kilogram meter per second. Right? Therefore, you have seen this unit before. It is a unit for momentum. Alright? It is a unit for momentum. Momentum, but we will say in this case, from this formula, we can see that impulse of an object is the change in momentum of an object. Okay? So, impulse of an object is the change in momentum of that object. Is the change in momentum of that object. Right? What I mean is that impulse is equal to change in momentum. Okay. So remember, impulse of an object is the change in momentum of that object. Where do we get it from? We get it from here. as you have seen, we said F net delta T is referred to as impulse. And we know F net delta T is equivalent to change in momentum. Okay, it is equivalent to change in momentum. All right, so the calculations here are no different. It's something that we have done before. It's just that right now we're using the term impulse. It is not different. You still have to use the very same knowledge that you used previously. Okay, perfect. Now, I believe we're going to the third item, which is impulse and safety. Impulse and safety. Oh, Nadine. Yep, impulse and safety. So I'm going to put some pictures as much as I can. Let me begin with this one here. Okay. And then I'm going to take, again, this one here. Don't be too large, buddy. Okay, don't be too large, buddy. And then, but before I proceed, I want to remind you, when we use impulse, or when we use impulse, we are going to refer to this formula where we say F net equals delta P over delta T. Our knowledge is F net is directly proportional to the change in momentum. Therefore, F net is indirectly proportional to the change in time. Okay, so maybe let me add these guys in the next page. I'm going to cut them and paste them in the next page. Okay, we're going to talk about that in the next page. So, and you guys, I can put you in the center, right? So, with the application of impulse, we say F net is equal to delta P over delta T, right? For safety purposes, items are designed so they increase delta T of impact, therefore, reducing F net, I'm going to say and F net and what? F net and change in momentum. Because remember when we have said, when you increase time, this is inversely proportional. When you increase time, you decrease the net force. So if your net force is decreased, or change in momentum will increase. So if your collision happened at a short period of time, the net force will be greater than when it happens at a shorter period of time. Okay. So these designs of the items I mentioned, let me go back. The design of these items is basically to say, whatever collision that happens, it should happen within a short. They're designed so that the collision is taking place within a longer period of time. Because if they happen within a short period of time, the collision is very fatal to the users. Okay, it's very fatal to the users. Now, let's go. I'm gonna show you something now. So, cool. So we said safety designs of these items I just mentioned are built in a way that they ensure that the collision takes longer. By taking longer, the net force or the force of impact will be reduced. Okay? Well, small now. So let's look at these pictures. I'm going to explain some few things on them. Here, these pictures have many safety features. Okay. For example, the first one is a car. I'm going to begin with the seatbelt. With the seatbelt, without the seatbelt, when the brakes of a vehicle are applied, the person or people inside the car will move forward. And when they move forward, they're going to clash or crash the steering wheel, the seats in front of them, and the windscreen. Now, if more unfortunate, they can even be ejected from the vehicle. And obviously, when they are ejected from the vehicle, they're going to collide with the ground, causing more damage or injury to them, and sometimes death. Right? And sometimes death. So they can lead to fatality. Right? So, without a seatbelt, the time taken for an individual to, say, collide with the steering wheel will be shorter. In the same case, on the same instance, the individuals who are passengers seated at the back, the time taken for them to hit the seats in front of them is shorter. But if they have the if they have seatbelts, if they have seatbelts, the seatbelt will sort of push them backwards, right? Slightly. It'll push them backwards. So it'll take longer than when they don't have seatbelts. It'll take them longer to hit whatever object in front of them if they end up hitting those objects. It'll take longer. Now, when it does take longer, what does it mean? It means the force of impact will be reduced. Now, if the force of impact is reduced, it means injuries are reduced. Right? Injuries are reduced is not to say they are eliminated. There will be injuries. Right? Injuries are reduced. But imagine if there were no seatbelts. That is simply because the time taken will be longer and the F-net will be reduced. The same thing can be explained using this airbags. With the airbags, without the airbags, during a collision or when a car stops, the drivers and the passengers will hit whatever that's in front of them within a short period of time. That will cause injuries and even fatality, right? But with the introduction of the airbags, the time taken for them to hit whatever in front of them will be longer, thus reducing the force with which they can hit these objects, or they can, they can be ejected off the vehicle. All right? This is what is happening with airbags. So obviously, or not obviously, yes, with airbags, the time of the collision, the collision between the passenger and the steering wheel or whatever object in front of them will take longer. When this happens, the force will be reduced, right? Thus minimizing chances of injury and fatality. Okay. Now, crumple zones. You have the front crumple zone and the rear crumple zone. During a collision, if someone bumps into your vehicle, before the car can deform the compartment, the passenger or driver compartment, it has to have collided with the crumple zone, which is basically an empty space. So this empty space will reduce the force of impact which you might have experienced if the vehicle didn't have a crumple zone. All right? It'll reduce the force of impact that one might have experienced if there wasn't a crumple zone. So, as usual, this means for the collision will be taking longer. Right? The collision will be taking longer. The collision here would be the other car bumping into our car. It will take longer to get to whatever. So before they can deform this passenger compartment, what is happening? It must have deformed or destroyed the crumple zone region. All right? So when it gets to the passenger compartment, the force will have been reduced, causing minimum damage to the passengers, if any damage or fatality. So it will have minimized fatality and damage. because the force has been reduced by increasing the time of the collision, right? The same applies to the crumple zone. Okay, now the very same thing is said about these pads. So with these pads, we thought these pads, if a cricket ball strikes your leg, it's gonna break your limbs, right? It's gonna break your limbs. So if a cricket bat strikes your legs, we thought these pads, it's gonna break your limbs. But with these pads, what is happening? What is happening is that they will collide with the padding first, and there's so that time that the ball strikes the pads basically reduces the force which you are gonna feel if there were no pads. So obviously, I said this reduces the force that you were gonna feel without the pads, right? So the force is reduced, and obviously the collision time between the ball and your leg is increased, right? Is increased. How is it increased? Because before, really, the ball can, let me maybe make a diagram. Let's say this is your limb, and then, okay, now let me make it straight. Let's say this is your limb, and then this padding provides, let me give it a blue color. So this is the padding there, and this is the padding there. And remember, without the padding, let me also add an object here. Without the padding, this is what would have happened. So without the padding, look at how easy it is for, can let me close? Look at how easy it is for the object to strike you. It's not stopped by anything, or what's the way that we can use? It's not absorbed by anything. But for here, before it strikes your leg, it must have penetrated the sponge, right? Before it strikes your leg, it must have penetrated the sponge, right? Or depending on the leg guards, right? It must have struck or penetrated. It must penetrate the padding first. So obviously, this is why we are saying the force here the collision time is long, right? Here is long, and the force, no, it's shorter here, not long, it's shorter, right? It's shorter. And here, the F net is, all about it, it's larger. But here, the collision time is long, and eventually, this means F net will be smaller, right? F net will be smaller. So this explains why they need these paddings or these guards, okay? The same technique is said about the gloves, right? The same technique is said about the gloves. The gloves, what is happening? The time taken for the ball to strike the hand will be longer, thereby decreasing the force of impact between the hands of the whoever, the batter or the catcher, the wicket keeper, right? It'll reduce the force of impact between their hands and the ball, all right? But without the hands, without the gloves, this cricket ball or whatever object that is projected can really injure a person's hands, right? It can really injure a person's hands. So we wear these gloves so that we prevent such injuries. When there are injuries, they will be minimal as compared to without the gloves. Okay. Now, you then head to the head. So to the head, we have the helmets. These helmets, as you can see, they have the helmet itself is made of a stronger material that ensures that the ball doesn't strike the head of the player, because if they strike the head of the player, the same technique you explained, it's very dangerous. You don't want players suffering of concussion and later brain damage and whatever. You don't want that, right? Or dying on the field. You don't want that. This is also the case with your biker's helmet. Okay, so this ensures that it's made of a material that ensures that before the object can strike the head of the player, that impact must take a bit longer so that the force can be smaller. Okay, so that the force can be smaller and not dangerous to or fatal to the player. Everything about this helmet is explained in the very same way. Okay. Now, let's then add some other parts. So by the way, going back to this applies to every glove. Goalkeeper gloves, wicketkeeper gloves, even boxing gloves. Boxing gloves are explained in the same way. Okay, so boxing gloves are protecting the opponent and are also protecting the attacker. Okay, the technique is the same. All right, perfect. Now let's also add. Let me see. Okay, we have goalkeeper gloves here. Let me add these guys. Okay, let me add these guys. This is an arrestor bed. I'm not sure of the. I like that. You see what I was talking about. So here they wrote arrestor in OR, and here it's in ER. Okay, so an arrestor bed, guys, is basically a gravel, as you can see here. It's basically a gravel or sand. Okay, it's basically a gravel or sand that is built or laid on the side of the road. Arrestor beds are used when the brakes of the truck are failing. Right? They are used when the brakes of a truck are failing. So obviously, when brakes are failing, if the truck had to drive on the tar road, it will be very fatal. All right. So we are saying reduce the impact that this would have to the driver by traveling in this long sand or gravel road. All right. So what is happening here is this: the truck will be traveling here for a very long time. All right. It will be traveling here for a very long time. Remember, he doesn't have control over the brakes. He or she, by the way, they don't have control over their brakes. So this long path or this long pathway, long gravel, will basically be forcing the truck to come to a stop. Now, the way it comes to a stop, it will not be one that is very dangerous or harmful or even fatal to the driver, right? Because you want safety of the driver. So now with the arrestor beds, they are long pathways. So with them being long pathways, the time taken for the truck to come to a stop will be longer. Therefore, this will be reducing the force that impact would have on the driver, right? Because if the truck had to stop without, say, in any other place, it will stop forcefully. That would be fatal to the driver. The driver would die, right? Or would be very injured, all right? And we do not want that. So rather, the driver drives here and the car stops gradually, right? So when the car stops gradually, the time is longer for it to stop, but the force is reduced over time, right? The force is reduced over time, right? And when the force is reduced, obviously the momentum of the truck is also put to a stop eventually. And when that happens, rather, the force that is exerted on the truck will be small. And when it's small, the driver will be safe. All right. So this is these are safety instructions or safety designs that we have. Okay, these are safety designs that we have. Let me go back to the opening page. Now, in the opening slide, we have, this is in Olympics. And sometimes this is in Olympics or whatever, Olympics or whatever. I don't know what you call them. Yeah, let's call them athletics. Okay? So, imagine if this lady was landing on the ground was landing on the ground. Chances of her being injured are very high, right? But right now, she doesn't land on the ground. She lands on this mattress. This mattress will somehow bring her contact to the ground wherever this mattress can be pressed to, because it has to sort of deflate a bit. When you land on it, it has to deflate a bit. Right? So instead of her landing on the ground, she lands on this mattress. What does it do? The force of impact between the lady and the ground will be reduced, because the time taken for her to get to the ground after landing on this mattress, the time taken will be longer. And when time is longer, the F net, or the force, what does it do? It decreases. Therefore, she will leave and she will land safely. Maybe let me say she will leave safely without any injury. The same thing is applied with stuntmen when they are performing their stunts in our action movies, right? They don't land on the ground. They land on a net or on a mattress, right? Because you still want your Jackie Chan's. You still want Jackie Chan to do his movies, right? Because he landed on a net or on the mattresses, right? Okay, perfect. Now, going to the fourth item. Now, the fourth item will be wet examples. We might try with, I think, one or two examples. So let's see wet examples. So example A, let's say a bed exerts a 12,000 Newton force on a ball for 0,007 seconds. Now calculate the impulse. Do you hear this? Calculate the impulse of the ball. Calculate the impulse of the ball. Okay, so this is easy. Our solutions. Remember, guys, impulse is a vector quantity. So the ball, we expected it'll move forward. So it's okay. I'll just say forward or away from the bed. Okay, so impulse, be careful of your answer as well, because already I can imagine instead of reporting your answer in Newton second, you report it in something else, which is the same, but stick to Newton second because it's impulse. So it will be F net delta T. So what is F net? It was 12,000. What is delta T? It was this impact lasted for 0,07 seconds. So what is our answer? 12,000 times 0,007 is, let's see, 84. So our answer is simply 84 Newton second. Where should I say? Away from the bed. Okay, it's fine. Away from the bed or forward, it's fine. Away from the bed. That is the impulse of the ball. Pay attention. The unit is Newton second. Okay. Now, let's try another example. This one says, a naked. How much does a shoulder launched project how much does a shoulder launched rocket's momentum change if it experiences a thrust of, I will write it down. How much does a shoulder launched rocket's momentum change if it experiences a thrust? If it experiences a thrust of 2,67 kilonewtons for 0,204 seconds. So to answer this question or to understand it, they can go either way, can go forward or backwards. But because we are giving the word thrust, it means it'll be forward. So we are looking for a change in momentum. I would begin by saying impulse. What I know, impulse is F net delta T, which is 2,67. If you are not sure, I like writing 2,67 times 10 to the 3. But for those that want to get this, to convert from kilo to Newton, we have to multiply by 8,000. Okay, you have to multiply by 8,000. So this will be 2,67 times 8,000. This will be 2,670. So it'll be 2,670 times 0,204. Let's get our answer. Cheers. Okay, 2,670 times 0,204. Okay, now our answer is 554,68 newtons. Allow me to say forward because this one, it experienced a thrust. So I'm going to say forward. Okay, I'm going to say forward. Now, change in momentum is equal to impulse, which will be 544,68 kilogram meter per second, where forward. Okay, forward. Okay, so this is it. This is how we draw. So this is it, guys. We have now covered almost every aspect of the 12 momentum and impulse. So let's see if we have answered the questions. So we were imagining if we did not have these things. We saw that without airbags, seatbelts, and crumple zones, during collisions, passengers will be in danger. They will die or they will be injured. We also saw that arrestor belts are very crucial for truck drivers because they help them to put their trucks to a stop. And mattresses, athletes and stuntsmen are so safe with these because without them, they can be injured and possibly die. Right? Your gloves, whether it's goalkeeper gloves, boxing gloves, and whatever gloves that you can think of that are used in sports, they are helping sports stars from getting injuries. Same applies to shin and leg guards, right? They are protecting athletes. Helmets, whether it's your biker's helmets or ones used in sports, it's also helpful. Now, we also have to look at the padded beds and racket handles. They are very helpful as well because they preventing injuries to players' wrists and palms, right? The same, we use F net equals delta P over delta T to explain this. So we have covered almost all aspects, and with that being said, I think it's a wrap, and see you next time. So, bye-bye.